So we stopped with discrete time Markov chains. The next part is our continuous time Markov chains, right. So again we will just give the highlights of it, and then I will move along to queuing theory, because that is where we should have been last week itself. Okay. So continuous time Markov chain, again the state space is finite, right. Or it is discrete, can go up to infinity, but with discrete set of values, right. And the time parameter is continuous, right. So the transition from one state to another can take place at any time. That is the basic definition, right. Whereas in the case of discrete time Markov chain, the transition was only at specified time ticks, time instants. Okay. So the standard definition of Markov chain again applies. The probability that, right, that you are in a current state, and if you have the probability going to the next state only depends upon the current state and not any of the past states, right. So or the past time. So the future is dependent only on the present and not on the past. That is the again classic definition for that, right. So if I want to represent this, it is basically this variable x, right. So x is the state of the system at time t, and that can, right, so that represents the your Markov chain as such, right. The t is continuous. Then we talk about transition probabilities. So we used that last time, right. So here we will again define transition probabilities first, but we will find that it is more useful to operate with something else. So this is probability or Pij in terms of v and t, where v and t are time units, right, is what is the probability that x of t equals j given that x of v equals I. So at time v I was in state I, and at time j or time t I will be in state j, okay. And this is for even equal to is also okay. Right. So again we talk about the instantaneous probability of transitioning from one state to another state, okay. So the Markov chain is fully defined by a given Markov chain, right, is characterized by the initial state, in other words the PMF of so T naught is the initial time, and at time what is the probability that x will take any one of these umpteen values, right. So that is the PMF, because x is a discrete set, right. So the state set is finite or countable. So that defines, that is one part of the definition as to what will be the initial distribution for the system to be in one of those various states, and the second is of course our Pij's. Okay, since I do not know how to change that, I leave it. Okay, so the book has some more other definitions for time homogeneous and all that. I will simply skip that. I just want to get to this so called Q matrix. You heard of the Q matrix, the infinitesimal generator matrix. I will just say generator matrix from now on. I can never get that right. Okay. So in the case of discrete system we talked about transition probability, so that made sense, right. But in the case of a continuous time space, we actually would like to look at the rates, the transition rates of going from one state to another state. So the rate is simply defined as the differential, right. So we define for I not equal to j, right. So that is the differential or partial differential of the transition function with respect to t, and then evaluated at v equals t. So this Qij is referred to as the transition rate. Then we will define at time t, right, this qt, which is for I equals there is a slightly different definition, but I will not go much into that. Okay. So we know the state of from one state to another state, what is the probability, but there is also a small probability you will stay in the same state, right, because this is looking at this is a very tiny instant t in t plus h, right, h is very small, h approaching 0, there is still a probability you will still stay in the same state. Okay. So the only condition that in this particular matrix that we have to observe is that so from a given state, right, the sum of all the transition rates should equal 0, which means the probability of staying in the same state will actually be negative, or the rate for the staying in the same state will be negative. We will see, we can actually derive that when we look at the birth death process later on, but for now the Qi's will be all negative, right, along the in this matrix, right, the diagonal elements will be all negative, that is the rate of staying in the same state will be negative, such that if I take a row and sum up all the values, it will end up being 0, right, because of the rate of transition from one to another. In the case of probability it adds up to 1, in the case of rate it is going to add up to 0. That is your basic balancing equation. Okay. And then for this the theorem that we will look at, right. So again I am using the term irreducible without the full definition. So what I am interested in is for this continuous time Markov chain, given the transition probabilities from which we can derive the transition rates, what is the probability of being in a given state at time t equals infinity, right, what is the steady state probability of being in a given state. So that is again defined by, so pi j is the probability, is the steady state probability of being in state j, right, which technically every instant of time this probability will change, but at time approaching infinity this reaches steady state, so there is going to be no variation, right. So this is the steady state probability just like we calculated for the discrete DTMCs before, right. So this PJs will always exist and this is for so how do we determine these pi j's? We had in the other case pi into p equals, or sorry, v into p was equal to v, right. That is the steady state probability in the case of DTMC, because there we use the transition probabilities. Here we are using this the generator matrix. So pi of pi into q, where pi is your vector, right, and so on, and my pi is kind of changing shape. So that is a normalizing condition, right. So the steady state probability should sum up to 1. These are the probabilities, and so I basically need to solve this equation, right? Just like we solved in the other case, pi v vp equals v. Here we simply solve pi q equals 0. Again, I am skipping all the. I am sorry. Oh, that's actually 0. And again, if you are keen on the derivations, you can actually go through this book here, but I am bypassing all that. I just want to get to the fact that if I give you a Markov, continuous time Markov chain, and I give you the transition rates of probabilities, then from that we can construct this Q matrix, and then bingo, we are done. And then if you can solve this, and if you have solutions for this particular equation, then you have your steady state probabilities for a given system, from which you can derive lots of other things, right. So this is what you want to do. Which one? Which one? Even for very large time there is no transition taking place, it is stable now. Yeah, so if you look at the steady state probability, because if you are trying to so this is pi 1, pi 2 and so on, right. Right, and this is okay, let us say q 1 1. So this is, and then this is probability of going from state 2 to state 1 and so on up to state n, right. Yeah, so this would be your the rates of transitioning from see pi 2 into q 2 1 is the probability that you are in this state, and the rate at which you will transition into this state, right. So the sum of transitioning from all these states, okay, so let us see where is the, I have a separate equation for that. Until I put the equation I can't get the explanation. This is so given a state j, right, the rate of transitioning to this state from all the other states, right. So pi I represents the state of being in state I, qij the rate of transition from that state to this state j. So the summation of all those rates should equal the probability of staying in the same state, which is actually I have not defined this is pi I q I 0, where I not equal to j. So that is again a balance equation that says that the rate of which when you are in a given state, right, the rate of entering the state and rate of leaving the state is going to be the same, and the rate of enter depends upon the probabilities of being in the different states and transition to this particular state, right. That is what this is trying to tell you. Makes sense?
So QIs are actually not.
Sorry, this is QJ. This is what happens when I don't look at the book very closely. Yeah.
The Qs are actually also time dependent, right?
Which one? The
Qs
yeah, okay. The Qs will be time dependent. So you assume it is time homogeneous, and then so a lot of assumptions I am skipping there. So that if it is the case, that is a time homogeneous system where when it is time dependent, yes. But if it is, then we say that the system stabilizes after some long time, then this holds true. Yeah. But that need not happen. Yeah. Yeah, in fact the more general equation would be d pi of by dt equals q of t, right, or no, yeah, this is, if you are keen, if you don't want to, if you don't want to know this, don't know this, but this will be what essentially what it will be, right. So this is the actual equation, out of which when if pi of t stabilizes, right, to some steady state, then d pi by dt goes to 0, right. So the rate of transition of there is no more change, right, when pi becomes constant. So that is why your pi cube becomes 0, but this is the actual equation, which I have simply skipped because mostly we are interested in steady state systems.
How does in continuous time Markov system we always say that it exists for the
Oh, for the irreducible, or did I skip some condition? Okay, yeah,
says it
actually it
always,
says if,
but in DTMC it may not be the case.
okay, yeah, this, yeah, there is a short proof for that, but that is if it is irreducible, then that is what they are claiming. We have to go back and look at the proof for that as to why, right, what the intuition for that is. For now we are just assuming that if you can get from any state, if you understand the irreducible definition is that you have a set of communicating states, right, which you cannot reduce any further. All states you can reach any state, from any state you can go to any other state with some non-zero probability after some infinite amount of time or some long time. In that case it claims that it is existing, right.
So what is q of t as t tends to n?
I am sorry.
We are saying pi q equal to 5, right? But q is
Oh.
time dependent.
Pi q equals 0.
Yeah.
Yeah.
But q is time dependent.
Okay, so that is what I am saying. If it is at steady state, then we are saying that the pi changes will not be there, and the q also will not change with respect to time. Again, if it is a time homogeneous system, we actually look at more in terms of the time interval than the time itself. The system change, the probability of going from one state to another state, this Pij Vt will depend upon the difference between V and t than actual t itself, right. That is called a time. Again, that I have skipped all those definitions for the sake of not confusing you further, but for a time homogeneous system these things will apply. If it is time homogeneous where the transition probability and rate depends only on the interval elapsed, right, then these things will hold, right. Because most of the systems we look at sort of meet these conditions, we are generally sidestepping all those definitions because I want to just get to the main result. Okay, so that is the first set of, right. So if you want to solve the, so we have now DTMC for which you can solve that equation, right, V into I minus P or P minus I equals 0, or this other one, right, pi q equals 0. So one of these two we will have to solve for pretty much each of the systems. So besides this Markov or continuous time and discrete time, then there is also, so in again continuous time Markov chain, the other definition which is that the amount of time spent in every state is exponential, right, because now if I look at my system state, we will look at an MM1Q, right, to begin with. So then some of these things will, so now let us actually get into some queuing models. So now we are getting into our queuing theory, and then I come up with the MM1Q, these things will sort of make sense at that time, okay, as to why each state the time spent is exponential, because in the discrete DTMC I said the time spent is geometric with probability that PIA is what we define. Likewise here the same thing will apply, the time spent in each state in a continuous time Markov chain is going to be exponential, okay, and the exponential parameter we will see how we can derive that as we go along. Will depend upon simply that QII, probability, the rate of staying in the same state, right. That is what will define the parameter for the exponential time spent in a given state. Okay, now we are going to do a slightly quantum leap to queuing theory all of a sudden, okay. So a queue, we will have to define some basic concepts here. So a queue is simply represented by a buffer and a server, right. So you have a few things, one is the arrival process. So that is, so a queue is characterized by a whole bunch of things, okay. So one is the arrival process, and then the second is the buffer capacity. Sometimes we talk buffer capacity, sometimes we talk system capacity. System capacity is the total number of customers in the system, right, including the ones being queued and the one that is in service. That is also referred to system capacity. If you look at a bank teller, then including the guy who is serviced, we will say total capacity of each queue is 5, right. So then this, as far as server is concerned, we can classify the system in terms of the number of servers, right. It can be more than one, and for every customer what is the service time, right. So we need to define the service time distribution. So what is the service time per customer, right, that can be either constant or totally random, or it could be exponential or some other, right, we are with hyper exponential, something of that nature, we do not know at this stage. Okay. Then also one other characterization would be the scheduling discipline, right. Usually we assume FIFO, but there are results for some other specialized scheduling disciplines also. Then there is one more characterization, and that would be the total number of customers allowed in the system, which is actually the buffer capacity. No, it will be MMMM. No, that is already there. Then we have the service time distribution. There is one more, which I forgot. My notes doesn't seem to have it. Yeah, okay. So besides that, there is also a notion of population size, which is what I said. Okay, we will see how that is going to make sense. Okay, when we get to this population size, we will see how it is different from the capacity of the system itself.
What is the population there?
That,
Where the demands are coming from, or the requests are coming from, or total people in system?
the total thing is the total number of jobs in the system. For example, if it's a closed queuing network, it's going to be finite, right? And so you might have a smaller capacity, but that, no, let me go back and look at that. I am not able to intuitively, right, explain that population size again. For closed queuing it makes sense, whereas in this case I have buffer capacity which tells me the total number of customers in the system. Besides that, having one more parametric size. Number of that comes in your number of capacity, the server capacity.
Buffer plus people getting serviced at
Is the population size. Okay.
Yes.
something like that. Is
Okay.
there.
Okay.
You
I will
also
add,
have those getting serviced.
including the ones in service.
Or is it that the things that enter the queue are entering from this population or something like that?
No,
I don't know.
this, if you consider the system, entire system, you have a buffer queue
Mm-hmm.
length, and you have one or maybe multiple servers. If you have the multiple getting serviced, so this is the total population in the
Total, okay, the total population, if I were to guess, is the total set of customers that can enter the system, out of which your queue can only hold some B plus M number of buffers plus the number of servers. But let me find a queue where the population size actually is necessary, right, and then it will make sense. Okay, so we have this so called Kendoll notation. Right, so it is arrival, service, so number of servers, buffer capacity, and then our schedule. So this is for arrival, this is the service time, this is the servers, okay. So many times you will only see 3 of the first 3 is the one that you will normally see, because often we assume infinite buffers, especially theoretical analysis. We want to see what the asymptotic capacity is, or performances, delay, throughput, and so on. So B is often set to infinity, K again is set to infinity, so it does not come into the picture, and scheduling, if it is not specified, is simply FIFO, first come first serve, right. So for example is right, so and then we use the M for memoryless. So if arrival process is Poisson, then it is represented by M because it is Markovian, and the service time is also exponential, that is what the second M stands for. So if the packets arrive according to a Poisson process and are serviced based, the service time is exponential, then we have a second M also, and 1 is the number of servers. So your sort of classical queue is an MM1 queue, right. So we use the terms M is used for Markovian or memoryless, and then we have D for deterministic, so deterministic is when you have fixed length packets, for example service time is fixed, so that will be D, or if your arrivals are uniformly spaced, right, there is no randomness, you have every 5 seconds a packet arrives, that is also deterministic. So DD1 will be deterministic arrivals, deterministic service time, right. So for example if it is voice, or if you are simply voice sample gets generated say every 100 milliseconds, so therefore that is D, and the packets are always 100 bytes long, and therefore your fixed packet size, so that is a DD1 queue, right. And sometimes we simply call it general G. So you find combinations MM1, MD1, MG1, these are the things that we will normally be interested in, because we can always pretend that the arrival is Poisson, and then we have closed form results for MM1, MG1 and MD1, that we always use as a first cut analysis, even if we do not know if it is, but MG1 we simply need to know the mean and the standard deviation of the service times. If you can measure that over some sampling, you can simply use that and plug that values into MG1 queue to get the delay results and so on. And GG1 is the worst case, where GG is your arrival is also unknown and some general distribution is being followed, and the service time is also some general distribution, right. So your sort of a family of would be say MM1, right, MD1, and then we go for MG1, right, and then here again we have some additional flavors where I might go for some MMM is also more interesting, right, where we have look at M servers. We saw some of these results, only the results, right, in the networks class, and the special case is where and then our buffers, right. So
No, MMM.
so from MM1B we can derive the MMMB, right, all those variations are there. So we have MMMB, so MMMB where B is sort of unrelated to M, but this is a special case where M equals the number of customers in system equals to the number of servers, right, and of course our sort of GG1 is the highly generic system. It's when your arrivals to if you go sit in the bank and you find that there you can measure the mean and the standard deviation, but there is no particular process that it is fitting into, right, and simply have those two, and likewise the service time also. Service time, for example, if you are looking at a queue, if you look at the packet length distributions, there is not necessarily exponential service time, right, there may be some distribution is being observed, and let us say only 10 different packet sizes are possible, and for each of those there is some histogram that is given to you, and that is a histogram, and that you can only measure it, that is about how you write over a 1 hour period of finding that, and so for that you simply use the GG1 results in terms of the mean as well as the standard deviation of what you are measuring. So that is usually when you have a set of samples and you cannot fit that to any particular distribution, right.
If you fit to some particular distribution, then there is some other category, right, it has to go into, you can't fit it into M, D or G right now.
If
I'm able to analyze theoretically.
If you are able to still analyze, but what we have usually is closed form for M and D. If it is something else, like if it is hyper exponential, then I would simply use again the mean and the standard deviation if you can compute that. So even if it is a known distribution, but closed form is usually available for one of these. I do not know of closed form for other types of distributions, right. The classic ones are these. So MG1 could be even if it is in some other known distribution, but for which you cannot get the closed form solutions, right. So you just want to get the average delay, which will be just mean is what you are interested in. For MM1 you can also find out other secondary parameters. You can look at the service time distribution or the delay distribution. We only calculate average delay, right, but what is the distribution of delay, that also you can try to find out in some cases. In some cases it is not easy to find. So it depends on whether first order metrics are sufficient, or if you want more detail in terms of what is the percentile of delay, right, what is the probability that 90% of packets will have less than, right, 100-second delay. Those things are harder to find as the other distributions. Okay. So that is our the basic classification of queues. Okay. Okay, so now let us see what we can do in terms of analyzing MM1 queue. Okay. So in an MM1 queue we need to figure out what will represent the state of the system and what are the transition probabilities or rates, right. Is this continuous time, discrete time, what is this going to be? So here you have customers getting added to the queue and then customers leaving the system, right, and so therefore we will use these terms. So lambda is the parameter for the Poisson arrival, right. So this is number of packets per second. So in general this is number of arrivals per second. Okay. Then mu is the parameter for the, so we will assume that this process, this is again m, right. So therefore the service time is exponential, so this is exponential So for an exponential distribution we used a before because I did not want to confuse, sometimes we also use lambda and so on, but now from now on it is going to be mu for the service. This is the capacity of the server. So the mu for a queue will depend upon two things, right. One is the average time that this person is that each customer will need in terms of whatever packet size and things like that. It also depends upon the capacity of the server, right, in terms of number of bits per second that it can send. That is the simplest way to look at it. It depends upon both things. Sometimes we just say that, okay, so this will be departures per second, right, or services per second. So it is actually not departures per second, but that is roughly we will call that, right. So this is the number of customers, so we won't use that, serviced per second. So note that lambda mu are both in the same units, right, something per second. So this is the rate, right. So this is the arrival rate, this is the departure or service rate, right, that is what we will call this. So this is the arrival rate, this is the service rate. So that is rate is basically number of customers it can handle per second. So some teller will be very fast if that is only simply cash giving teller, or if it is a DD teller then more processing is needed, therefore there will be only 3 customers per 10 minutes or something like that, right. So that is simply capturing the capacity of the system, the arrival rate and the service rate, right. This is the, and there is only one server in the system, okay. If that's correct. Yeah, this we assume there is only one server, so I am just looking at one particular, say DD counter is one counter, that is all we are looking at. When you look at multiple counters, that we will have a little bit of analysis. This is only single counter that you are looking at, and we know that this counter can handle X number of customers per second, that is all. So now to represent this as a Markov chain, right? Somehow we know Markov chain, so everything is a Markov chain, right? So what should be the state of the system? No, what is the state? Not the Q0. What? The number of customers. We saw this earlier on, right? So the number of customers in the system is the state. So the state is a discrete set. So the possible states are 0, 1, 2, 3. If it is infinite Q, I can go up to infinite customers in the system. So therefore it satisfies my Markov chain, well at least the chain property, right? The set of states is finite, okay, or countable. So then, we start off with state 0, state 1, all these fellows we will draw, and this goes on up to some state I and then so on, right, infinite. Okay. So now is this a continuous time or discrete time? Only continuous time, or can it be also discrete time? I can also model this as a discrete time system where I take a very small interval delta t, right. Then if I am in state 0, from any state to any state, we will use something like what we saw in that aloha probability, right. So I need to know what is the probability of getting one packet in some small delta t, right. So delta t is my time, they even call it t to be simple, right. So t is approaching 0. Then I can also model this as a discrete time. So every t, every 1 nanosecond I look at the system state, right. So mostly I will be in the same state with some probability, small probability they will have one packet, right, and the probability of getting one packet, more than one packet in this 1 nanosecond is presumably very small, right, if my lambda is sufficiently small. If my lambda is a million, then of course I can get several packets in 1 nanosecond or 10 million. So I can model it that way, right, as I look at the system at every nanosecond and model it as a discrete time process. That then we can simply have to compute this transition probabilities and we can simply solve, right, that is one way of doing that. Okay, we will try both, let us see if this the second one. So that is one. The other is to look at this as a continuous time system where at any point in time I can go from state 0 to state 1, okay. So what is the time spent before so what is then we have to look at this whether this Markov property holds or not, right. So what is the distribution for the time spent in a given state? Let us just look at state 0, there is no customer, right. So I am looking at the time required to go to state 1, right. There is what is that inter-arrival time, right, that is simply so when to go from one state to another state, the time is simply the inter-arrival time between subsequent customers or packets. We know that the source, the arrival process is Poisson, and we know the relationship that if it is a Poisson arrival, the inter-arrival time between, right, two consecutive arrivals is exponential with parameter lambda, right. So therefore this state 0 I can, so this is basically a continuous time. If you look at it as a continuous time system, the amount of time spent in state 0 is exponential with the parameter lambda, okay. Okay, so that is one part of the story that we have now thought so far, right. So now here actually we will find that it is easier to define the transition rate. What is the rate at which I will go from state 0 to state 1? I can simply say lambda, but we have to do some justification for that, right. So the rate of transitioning from state 0 to state 1 is simply defined by the arrival rate, right. So with rate lambda I will be going from state 0 to state 1. We can later on derive the discrete probabilities, will be a little more intuitive, but let us look at this, right. So here I am looking at a system where I go from state 0 to state 1 with the probability lambda. Likewise in state 1 I am servicing a customer, right, the service time is exponential. So the amount of time I will spend in the same state is simply exponential. So if anytime I can simply go back to saying that I have finished, the customer has finished service, and I switch over to state 0 with rate mu. Okay. So why do we call this the rate? Because the okay, actually for that I should go back to the definition. But if you look at it, the number of customers, right? No, actually this should be the probability. Fine. Yeah, that's okay. I'll next time I'll try to work out the probabilities, right? When we have it. The rate at which, yeah, lambda and mu is the rate of arrivals, mu is the rate of service, right? So for the rate of transitioning from one to the other is simply is lambda mu. Okay. So for now we'll just, so to go from here to here, again it's lambda, from here to here it is lambda. So now this is your simple birth death process. Okay. So to go from one state, you only go to neighboring states always, because right, because there is only one arrival that will come, right. So one arrival comes, you go to the next state, and the rate at which an arrival comes is defined by this parameter lambda, right. And likewise you will go from 5 customers in the system to 4 customers when one customer finishes service, and the rate of finishing service is simply the service rate of the system, right. So with rate mu you will go to the neighboring, to the one state below. Okay. So this is, so but unlike the example that we saw for the DTMC birth death process, there is no self loop in this particular case, right. Why is there no self loop?
Because probability is 0, right, staying in the same state.
The probability is not 0.
No, rate.
Rate is not 0, rate is not, the summation of all the rates is going to be 0. So I am not showing the self loop because that is implicit in the definition that this is a discrete. So it spends a certain amount of time in a given state with a particular rate, right, and that we will see how we can actually get that. Okay. So this is my basic, right, rate equation. Okay. So if I were to look at this matrix, so I will, from 0 to 1 it is lambda, this will be minus lambda, everything else is 0. This I am simply using that as the row elements, right, the rows of or the sum of elements in a row will add up to 0. So the rate of transitioning from 0 to 0 is given by minus lambda. So the rate of staying in the same state is minus lambda, the rate of going to the next state is 1. Okay. So from 1 to 0 I will go with rate mu, 1 to 2 I will go with rate lambda. So what is the probability of staying in the same state is minus lambda plus mu and so on. Okay. So now this is lambda plus mu, right. So this is of course intuitively same makes sense because the rate of being in a state, right, the transition rate should all add up to 0, but does this lambda plus mu have some other significance also other than simply say I know this is lambda, this is mu, therefore it adds up to 0, therefore I am choosing my mid element to be minus lambda plus mu. Okay. So let us look at the state 2. Okay. State 2 I have 2 processes happening, either an arrival comes, therefore I go to state 3, or a departure takes place, therefore I go to state 1. And these are both exponential processes, right. This is with the parameter lambda, this is with parameter mu. So I will leave the state 2 when the min of these, right, when the first of these 2 events takes place, I will go to the, I will leave the state, right, whichever state I go to, lambda plus mu is, right, lambda mu or rates of going to either this state or that state respectively. So if you remember our tutorial, right, min of 2 exponential variables, we worked it out 2 weeks ago, right. So if x equals exponential, or x1 is exponential with rate lambda 1, x2 is exponential with rate lambda 2, right. So we saw this one. If I have 2 such variables, right, so 2 events taking place, and if I define x to be the min of x1 and x2, right. So what was x actually then? We said there is also exponential with rate lambda 1 plus lambda 2, right. So that is why here, so actually the rate of leaving the state or staying in the state is yeah, rate of departing is lambda plus lambda, therefore the rate of staying is simply minus lambda plus mu, right. So with rate lambda plus mu I will either go to one of those two states, that is what these two arrows indicate, right, and therefore because I am talking of rate of staying will be simply negative of that. So same just like in the case here, right, lambda minus lambda equals 0. Okay, so now this is my Q, right. So assuming that steady state probabilities will exist for this particular system, I can try to solve my phi q equals 0, right. So basically I will say pi naught, which actually it should be, technically speaking I should have a finite matrix, right, but let us assume it is somehow finite. I am sorry, which one?
If you assume a finite,
Finite, the last one will, the last one will be simply
mu, no,
mu
lambda
and minus.
minus p.
Okay. So just to be consistent with the book's definition we will use from now on, right, let I want to use that pi be the steady state probability of being in state I. So if I simply multiply that matrix and you start, right, you will see a bunch of equations popping out, one for each state you will have an equation that is popping out, right. So what is the equation for the first state? So for the first state this is P naught zero to 1, yeah, so this is mu right, and then 0 mu and so on. This equals 0, right. So what is the, so from the, for taking this okay, the first step of the multiplication would be minus lambda p naught plus mu p1 equals 0. So this is your first so called balance equations, right. So this is basically telling you that the rate should always sum up to 0, right. So therefore mu p1 equals lambda p naught p1 equals right. Now of course I have to do some definitions which is kind of skipped in the beginning. So we will let, right, rho equals lambda by mu and rho is less than 1. So your arrival should always be less than the service, otherwise what will happen to this system? It will just, if lambda is larger than mu, then you will all in the long term you will never come back to steady state, right. You will always be approaching infinity because you always have more customers arriving, you will simply keep jumping to the future two higher states, and you would never come back to a steady state. So you will always have infinite q, right, infinitely large q, and the probability of being in any state is going to be essentially 0. So that this condition is needed. Okay, so my first equation gave me this balance form, right. My second equation, so this is my second balance equation. So how do you simplify this? So lambda p naught is also equal to minus mu p1, right, we saw that last time, or equal to mu p1, sorry. So this is mu into p1 minus therefore mu p2 equals lambda p1 p2 equals